Hey, good afternoon, everyone. We are going to our last chat room and fact of the semester, and I would like to give you a few tips with respect to final exam next week. So, final exam, as you know, it's in the syllabus, and maybe all of you already. It's going to be done in LA 232 at 10 a.m. On a Thursday. Now, in case you cannot attend this final exam at that time, you can communicate with me. We can try to arrange something else. What I recommend you to do is to check my schedule. I have office hours and I also have classes. And in my classes, I will be delivering final exams. So you could join with me in my other classes and take your final exam. I will be doing a final exam also for some students that cannot attend 10 in the morning in one of the computer labs if I have access to, and that is SA111, SA115, or the tutoring center. So you have to communicate with me. I have one student so far that is coming on Tuesday at 6 p.m. So if there are another student who would like to take final exam at the same time, just go for it. But please communicate with me because I will not have the entire lab for my class. I will have part of it. So I have to share the space with other professors. But just to accommodate you, allowing that to happen. The second point I would like to remind you about is we don't have a discussion this week or Astro News. So the moment is a moment to get ready for final exam itself. And then you might be asked, okay, what should I do to prepare for the final exam? So if you go to your course, and I think, let me start sharing the screen just a second. So if you go to your course and go to modules, in the first module, there is a link that is called Tips About Exams and Final. So if you click on it, it will take you to the first chapter of a book we are, or some of us are currently using, Understanding Our Universe. And then if you select one of the chapters, for instance, if I take chapter 10, that is about measuring the stars, where we deal with these parallaxes and spectroscopy and the use of spectroscopy and photometry to derive chemical properties of stars or how fast they are moving away from us and towards us. So you always have a diagnostic quiz. And then you can take easy or tough with 25 questions. And then you have a bunch of questions in there. So I would think this is a nice way to test yourself and to validate your knowledge. Some of these questions require Wikipedia. So if you go to Wikipedia or one of these read-on websites, you can find the answers right away, but you know our exams are not like that. So you have to know the subject. But going through these quizzes, it helps you to become, first, more familiar with the subject, and second, to be more prepared. So this is one of the resources I recommend. And some of the questions in the final exam, I kind of will inspire myself on those questions. Okay. Another option that I also recommend you to do is especially if you are not happy with your midterm grades, is to do the makeup exam. And then you might be asking, what the heck is the makeup exam? So the makeup exam is as you know, I don't do makeup exams for students who miss the exam. In fact, if you were sick or something, I have another opening time, which is usually on Saturday. But if you miss on Thursday and if you miss on Saturday, then I can't do much. But sometimes situations happen and we miss, and all the communication I do goes to the spam box, and then you ended up missing. So what I have in all my classes is what's called makeup exam, which is open to all students. So this makeup exam is going to be open this Thursday. In fact, you already could see in your course. It's called makeup exam, and then you click on it, and then you do it. So the way this will count towards your grade is I will take the makeup exam grade, compare with the exam grades of the 3 midterms, and I will replace the lowest score in this on the 3 midterms if the makeup exam grade is larger. So you don't lose anything. If you don't do makeup exam, it's not going to affect your grade. If you do and it's lower than the lowest score you got in previous exam, it's not going to affect your grade. But if you do it and your grade is bigger than, let's say, your lowest score, then I will replace that lowest score. And then I will average the remaining 3 midterms. So yes, I recommend you to do. It's a good thing to do. Okay. Now, this week we are kind of closing up our course, and a little bit of review of the steps we took to this week's subject, which is the Big Bang Theory and cosmology. The Big Bang Theory, not the show, but the astronomy Big Bang. You know what I'm talking about. But basically, we start our course looking up to the skies, and then realized there were certain types of changes and movements that need explanations. And in fact, if we go back 3,000 or 4,000 years ago, and our book is very good on that subject, which we call ethnoastronomy or archaeoastronomy, we realized that 3,000 or more years ago, we knew there was bright points of things in the sky we now know as stars, and also some bright sources of light that we thought were stars, but now we know are not stars. But these bright points have independent motion with respect to those other stars. And it took 2,000 years of deep thought process and modeling for us to realize that those wanderers were in fact planets, and come to the worldview that we embraced after the 1700, which was one where the sun was in the center of a solar system, with the planets going about the sun with elliptical orbits, and then we could explain all the changes we see in the sky as being the result of Earth rotating around its axis of rotation as it goes and revolves around the sun in a yearly basis. We can explain the apparent motion of planets we call prograde and retrograde motions as being the result of this relative motion of planets around the sun. So prograde motion is the natural motion of planets in respect to the background stars. They seem to go eastward. In retrograde motion, it happens when planet Earth is passing by these planets in its orbit around the sun, and then we see the planets now shifting westward during a few weeks, and then they go back on track on their prograde motion. So we saw that, and we spent a good deal of time trying to understand how these different motions come about. And the third major one was precession, which was caused by, first of all, Earth. As Earth rotates or spins around its axis of rotation, the planet oblates a little bit. And the combined tug of Sun and Moon over on the equatorial bulge of Earth, it gives rise to this wobbling process that takes about 26,000 years to complete the cycle, and we call that precession. So we saw, in respect to precession, that we, 2,000, 3,000 years ago, more precisely 3,000 years ago, we built up a system called astrology, by which we thought that stars would rule our lives. And stars would be kind of gods or deities with some supernatural power. And depending on the configuration of stars and their planets, certain actions would be more favorable to happen than others. And we know this makes no sense as we bring scientific information into the mix. So the position of planets and the interaction of planets and the influence of planets and stars on us are insignificant. I can't measure the psychological impact of configurations, and that might have something to do with astrology, I don't know, but certainly physical influence as the one that causes measurable changes is really not there. And one of the major proof to that is precession of equinox. So if somebody is born in March 21st and say, hey, I'm Aries, and because of that I have headaches and I have big horns and things like that, and I'm passionate in my love affairs. So it doesn't make sense, because if you're born in March 21st nowadays, the sun is not against Aries, but against a different constellation, which is Pisces, because of precession of equinox. So all of these little changes we saw, and then we culminated in chapter 4, in which we introduce light as the most important carrier of information in the universe. I mean, how do we know what we know about stars and about galaxies and quasars, and the universe started in a Big Bang? How do we know all of that? Because we know how light behaves, and we know how light interacts with matter. And as light interacts with matter, matter imprints on light certain features that if you go on track to be an astronomer as a student, you're going to learn to interpret these features, which you can control in the laboratory. So we don't bring stars to our laboratory. In fact, we use light that has visited those stars. We use light as the mechanism, as an ambassador that gives us information about the environment they were either produced or they interacted. And what are the main tools astronomers use to infer properties of stellar objects and galaxies and everything we know about the universe? Spectroscopy and photometry. Those are two very important tools. So spectroscopy is the technique that we take white light and we spread out in a rainbow, and then we analyze in detail, especially if we have what is called spectral resolution. We analyze in detail all those features that exist in the rainbow. And then we might be able to see absorption lines or emission lines, and sometimes those emissions or absorption lines have features on it. And then by modeling these features, we can say all kinds of things about metallicities and temperature and rotational rate, and checks all that information with more techniques, with more tools. Photometry is the technique by which we measure the light we receive from stars, from galaxies. We measure its intensity. And as we later found, the technique astronomers use laterally to prove the existence of over 3,000 exoplanets out there. Most of these exoplanets were found using Kepler's photometric techniques. Kepler is a satellite, and the satellite is facing a particular part of the sky, which is in Cygnus, and as planets cross by the disk of stars, it produces a dimming on the starlight, and astronomers can not only try to measure the dimming factor, but also the profile in which the light goes down, and by doing so, they can infer the ratio between the size of the planet, the size of the star, and some other properties. How far the planet is from the star can also be determined if spectroscopy is done concurrently. And then we study stars. So we move out. So now we have the tools of astronomers. We know photometry and spectroscopy, and then we go out and we use these tools to study stars. And then we find that stars evolve. Stars are formed out of gas and dust that exists in the galactic plane. And depending on the mass of the star, that was one of the most important discussion points we had. So stars evolve, they are formed out of gas and dust. They, as gravity takes over and bring the star to a hot center, and becoming therefore self-luminous, and we can see this light. So eventually the core of the star will be so hot and dense that will ignite fusion reactions. And these fusion reactions will produce new elements. The stars start out with 75% of hydrogen, 25% of helium, and trace amount of metals. But as the star evolves, hydrogen in the core is depleted into helium. And if the star is massive enough, that helium will be depleted in carbon, oxygen, neon, silicon, and magnesium, and so on, and so on, and so on. And if the star is massive enough, which means more than a solar mass, that star will explode, and this explosion will synthesize all the metals, all the atoms. When you look around the room you are now, all the metals you see came from that star. And this is right there is an impressive piece of information that I would like you to take for life. Don't think that stars are too far away from us. The stars are here because the mass that make up your body, that make up the table or the computer you're holding, the silicon chips you have in there, wafers. So they are all produced within stars that no longer exist. And our sun picked up that material and make up the solar system we live in. And then life developed in a ways that we don't know yet, but in 3 or 4 years maybe, James Webb Telescope will be able to bring some new information about exolife or life in exoplanets. And then we studied galaxies, which were collections of hundreds of billions of stars, our Milky Way galaxy with a population of 200, 300 billion stars. And then we learn that galaxies do not live independently. In fact, they assemble themselves in clusters. So there are rich clusters of galaxies and poor clusters of galaxies, but galaxies everywhere. And now we are in the last of our class with the Big Bang. So curiously, the great Albert Einstein, he had predicted a cosmological model, a model for the universe that was not the way we think it is nowadays, one that is expanding, one that is evolving with time. So Einstein had an idea that the universe should be the same now as it is in the future, or as it will be in the future, and as it was in the past. The universe doesn't change, so you have stellar interactions, you have modifications here and there. Maybe you have galaxy interaction, but the universe is just one thing without beginning, maybe. And for his surprise, Hubble, based on the knowledge we saw in previous classes, Hubble determined that the universe was expanding. How did Hubble figure that out? Well, he collected information about distances to galaxies, and for those galaxies he had measured distance. He measured also with Milton Humason. He measured the receding, the Doppler shift of these galaxies. And as a result, he was able to build a graphic which is called the Hubble flow. The Hubble flow is a graphic that relates, let's see if I have it here, probably I do, probably I don't, no I don't, no I don't. The Hubble flow is a graphic that relates the distance of two galaxies and the receding speed of these galaxies. And the way it goes, and the way we interpret this information is that no matter which direction you look, the universe expands in a uniform way. And how do we measure distance to these galaxies? They are so far away. Well, we use supernova, which are these exploding stars. In fact, and more primarily supernova type 1, which is the result of a binary system of a white dwarf with an evolving star. And these supernovae are so luminous that sometimes they outshine the entire brightness of a galaxy. Here's an example right there. So the amount of energy that is suddenly released matches out the luminosity of a galaxy, sometimes more striking here in this example. So because they are so bright, and because we know the amount of energy exploded in or released in a supernova, then we can, if we know the amount of energy, we know the luminosity, we can use the inverse square law to determine distance. And then astronomers found that, in fact, as of now, the universe is not only expanding as a result of Hubble flow. Somebody's in there. Who that is? Just a second. Hey, Thor, how are you doing? Good. I'm just going my monologue here, going over the Hubble flow and dark energy. I can hear some background sound on where you are.
Okay, I'm trying to lower
this. So and as it is now, the universe not only expands but also accelerates. And this acceleration is, oh, you really have a background sound there.
Okay, I'm going to disconnect.
I mean, you. All right. So, and it's an acceleration, and when there is an acceleration, one of the things we learn in physics is you might have a force responsible for it. Like when stars explode, it's because you have some there is some imbalance of pressure between one pressure is caused by the weight of the star against the core itself, and the other pressure is caused by this outward energy that propagates towards the surface, energy itself that is produced in the core. When there is an imbalance between those two pressures, so there is a movement of gas from the high pressure region to the low pressure region, and if the high pressure region is in the core, the store expands. So think about the same idea happening in the universe and switching the notions of gas pressure by the notion of superclusters of galaxies. So if you observe superclusters of galaxies and there is some expansion and acceleration going on, so you have to come up with some source of energy responsible for that. So astronomers don't know what that energy is, and then they call dark energy. So dark because we don't know, and there are theories that attempt to explain where that energy comes from. But primarily, a large percentage of the energy, between 75 and 80% of the energy in the universe comes from this dark energy. And then you have 15% or so of energy accumulated or stored in what we call dark matter, which we studied in the realm of galaxies. So dark matter, which the primary candidate is the weakly interactive massive particles, WIMPs. So dark matter is restricted to the halo of galaxies or to the environment where galaxies interact. And when the groups that simulates galaxy interactions of galaxies, they had to populate the environment with dark matter to make the simulations work properly. So 15% or so of the energy, the universal energy, is dark matter. So 75 to 80% is dark energy, and 5% or less is made of stuff we know, like protons, neutrons, electrons, atoms, and light. And that's what we see. So if the universe, as we observe, expanded, if you roll the move back to on time, you might expect all of that we observe, all the energy, all the light, all the matter, all the dark matter, to be concentrated in what astronomers call a singularity on a certain period of time. If you go to the Hubble flow, you can estimate that to be somewhere around 13 billion years. And if you can use more modern techniques, you can go to a more precise determination of that. So the scenario, so what's happening in the future, it's not a crystal ball, but it's in the realm of predictions. So there are theories that suggest that the universe is accelerating, which is pretty much pumped by dark energy, but eventually this dark energy will switch phase, and it will, instead of expanding and accelerating out, it will contract and pushes in, having some behavior not so much different from gravity. So as it's crunched in, it might bring again to a big, so-called big crunch, the big crunch. So you have the Big Bang and you have the big crunch. And another scenario is that the universe will just keep expanding forever in this accelerating universe, and dark energy will not change its phase in trillions of years. And if dark energy keep just expanding, so dark energy is something funny. In gas in general, when you expanded the volume where gas is, the temperature, which is a way to measure energy of the gas, diminished because you are expanding out. And and the vibration of molecules diminish because you have a bigger volume now. Dark energy has a different behavior. As the universe, as space expands, so this energy does not fall down. In fact, just keep on adding to the universe. So if this is some future for our universe, if this is what will happen, one of the scenario is sometimes termed the Big Rip, which means, well, the expansion will keep on accelerating, and now we will stop seeing the clusters of galaxies that are far away, because this expansion will move them so far apart that their light, their radiation will not have time to reach us, because the space is stretching in between those clusters and us. And if that keep on going, so eventually, and this pretty much is trillions of years, so our solar system by then will be gone. That eventually, if Andromeda and galaxies are still separated, which we saw last chapter, that's not the case. In 4 billion years, we will be all together. But Andromeda galaxy would pretty much be separated, and then eventually all stars would be separated, and eventually all the planets in our solar system would be separated, and eventually all atoms that make up our bodies would be ripped apart. That's why it's called the Big Rip, when dark energy becomes so overwhelming that is able to even strip electrons and protons and nucleons out of their atoms, and then the universe ended up with this very cool and expanded system. So there are different scenarios depending on which model you like to read, and then you can do philosophy basically on any of these models. The Hubble Ultra Deep Field was an impressive image that was done by the Hubble telescope, where the Hubble was allowed to point to a region in the sky devoid of any information, no stars and no galaxies that people knew. And Hubble stayed observed in that direction for several hours. And as a result, when the image was finally released, it came this Hubble Ultra Deep Field, which revealed that in every single speck of space we can think of, there are several galaxies. So these galaxies happen to be very far away, but not only that, they have some weird shape because they were very young. They were not completely formed yet. And James Webb Telescope will be, as one of its primary goals, is to observe in detail the very first generation of galaxies, because the light, the optical light of first generation of galaxies by now are pretty much shifted towards the infrared, where James Webb Telescope will have its optimal reception. So we might be able to get some further information. Associate also with the Big Bang is first ideas and theories of the Big Bang, or the universe started in a very hot and dense stage, came up before even Hubble. So there was theoretical approach made by George Lemaitre, was an abbé, and he gave the idea of the primeval atom, which was a big, atom, kind of in space, and suddenly that thing exploded. So again, Big Bang is not an explosion, but that was the idea of Lemaitre, and calculations of the nucleosynthesis that happened between hydrogen fused to give helium in the Big Bang was first done by Gamow and collaborator and there is a famous paper called Aleph, Bet, and Gamov, in which they explain all these details of nucleosynthesis. So see, when the universe started, you have energy and protons, basically. So quarks gave rise to protons. Protons are the nucleus of hydrogen, so it didn't have helium. But when, in a very short period of time, in fact less than 3 minutes into the life of the universe, the conditions of temperature and density were such that protons, which means hydrogen, found its way to form helium. And based on if you add expansion in this state, you can, with very good physics and very good mathematics, predict this 25% of helium we had in the universe as a result of Big Bang. So Big Bang theory is not just a theory out of the brain of few people, but is a theory that has valuable data that you can verify. And one of these data is the universal abundance of helium. So the universe started with hydrogen, but with the sudden expansion of this Big Bang and the temperature and density, it gives the right conditions to produce the 25% of helium we have in the universe. Right? If the expansion were too fast, which means if the energy released in the very beginning were too high, then we would not match this universal percentage. And if the temperature were smaller than it is predicted, then we wouldn't have the 25% of helium. So it's all nice tidied up. But basically, this 300,000 years to 700,000 years is an important date in the life of our universe, which is the time cosmologists call the recombination time, is when the universe cools down to the point that electrons can again recombine with protons, forming atoms of hydrogen. And when hydrogen is formed, hydrogen is helium is now trapped in hydrogen, and then light can escape. So it is said that was the moment that light traveled to the universe. So light was being emitted by a gas nearly of 10,000 Kelvin, and that radiation equivalent to that gas is now observed in the range of 3K, of 3 kelvins. And that is the so-called microwave radiation that was also observed by these two gentlemen, Wilson and Penzias, that got a Nobel Prize. In fact, they got a Nobel Prize discovering something by chance. I mean, they were skillful observers. They were using a microwave antenna, the one in the background over there, to relay information to a satellite, and they were dealing with this noise in the antenna. They didn't know what it was, and then they cleaned the antenna, and they found the pigeon poop, and they collected the pigeon, they released them far away, and they couldn't make sense of the noise. And then somebody who knew, there was a group, Robert Dick, I think that's his name, in Princeton. He was, in fact, submitting a proposal to get money to build an antenna like that. He calculated the radiation to be somewhere around the 3 Kelvin. So he was in a meeting with his collaborators, finalizing details of this project, when somebody called him and relayed the information that these two gentlemen had found some noise, and if that had anything to do with cosmology, and right there, so his project was over because these two guys found it. But it's funny because they got a Nobel Prize. They were not looking for that, and they were awarded the toppest prize in science, whereas some other researchers knew about it, were trying to get money to build the instrument, but they didn't. So sometimes science works in funny ways. And this is the 3K radiation. In fact, the 2.73 is not 3, but we call 3K radiation. That is a nice Planck curve, which implies the radiation we are being bathed by this 3K radiation from everywhere. And in old TV tube, you could see those flashing lights. Some of them would be this 3K radiation, pretty much impressing the tube. More modern satellites with better resolution can even produce sensible information on this 3K radiation, like seeds of galaxies information, and here it is. So the cosmic microwave background and the Wilkinson anisotropy map are an example of it. So all these little dots here represent light that is either being delayed or liberated by a gas, and by looking details of these dots, you can match out the seeds of galaxies information. So in all of this, the Big Bang, again, the Big Bang Theory, which is an enterprise that has more than 100 years since its very beginning, has been confirmed and improved along these 100 years, and to the point that now we have a very concise and consistent model. And up to the point that something better comes along, that's what it is. That's what we got. All right. So as I mentioned in the beginning, in this week we don't have discussions or Astro News. Just get ready for final exams. Contact me if you can't attend the final exam at 10 a.m. on Thursday. And for those of you who are graduating on Thursday, my congratulations. All right. And that's it. So let me stop the taping for now.